Ever wondered how AI systems process information like a human brain? Today, we're diving deep into the architecture of neural networks, exploring how layers of artificial neurons mimic biological processes to solve complex problems. This isn't just theory. It's the backbone of everything from self-driving cars to medical diagnostics. Let's break it down. At their core, neural networks are mathematical models inspired by the human brain. Each network consists of layers: an input layer, one or more hidden layers, and an output layer. Think of the input layer as the senses, receiving raw data like images or text. The hidden layers perform computations, and the output layer delivers the final result, such as classifying an image or predicting a value. Here's where it gets technical. Each neuron in a layer is connected to neurons in the next via weighted links. These weights determine the strength of the signal passed between neurons. During training, the network adjusts these weights using algorithms like gradient descent, minimizing errors through iterative feedback. This process is akin to a student learning from mistakes. Each iteration brings the model closer to accuracy. But wait, why do we need hidden layers? The answer lies in non-linearity. Without it, a neural network would merely be a linear regression model, incapable of handling complex patterns. Activation functions introduce this non-linearity, allowing the network to learn intricate relationships in data. Common activation functions include ReLU, rectified linear unit, which outputs the input directly if positive, otherwise 0, and sigmoid, which squashes inputs into a range between 0 and 1. The choice of activation function depends on the task. ReLU is popular for hidden layers due to its efficiency, while sigmoid or softmax might be used in output layers for classification. Now, how does the network actually learn? Enter backpropagation, a method for calculating gradients of the loss function with respect to each weight. It works by propagating errors backward from the output layer to the input, adjusting weights using the chain rule of calculus. This is where the magic happens. The network learns by fine-tuning its parameters to reduce prediction errors. Optimizers like Adam or RMSprop further refine this process, adapting learning rates dynamically to navigate the loss landscape efficiently. Imagine climbing a mountain. The optimizer adjusts your steps to avoid getting stuck in valleys or overshooting the peak. Today's neural networks power breakthroughs in natural language processing, computer vision, and reinforcement learning. But they're not without challenges. Issues like overfitting, when a model memorizes training data instead of generalizing, and the black box nature of deep networks remain critical hurdles. Techniques like dropout regularization and attention mechanisms are pushing the field forward. Neural networks are more than just a buzzword. They're a transformative technology reshaping industries. Whether you're a researcher, developer, or curious learner, understanding their inner workings is key to harnessing their potential. If you enjoyed this deep dive, hit subscribe for more explorations into AI's cutting edge. What's one question about neural networks you'd like us to tackle next? Drop it in the comments. Let's keep the conversation going. Thanks for watching. Stay curious and keep exploring the future of AI.